All right, I think it's time for us to return from the coffee break. I see Marie is getting ready.
Hi, yes, Maria, I'm here.
Okay, Marie is getting ready. Okay, perfect. It's just I can't really see myself, so I'm taking over Cecilia. I am Maria Sokolico, working with Cecilia at Imperial College London, and I'm going to be chairing this session. I am absolutely delighted to invite all our speakers. Before we begin, the only thing that I really wanted to remind you is if you have any questions during the talks, please feel free to post them in the chat. Otherwise, raise your hands after the talks are finished, and I'll ask you to ask your question. Okay, if for some reason I cannot see your raised hand, please do not hesitate, unmute yourself and ask the question. So right now, I do believe we start with Maria Crespo, and she's going to be giving us some updates on lignin-derived electrospun mats incorporating graphene oxides for sodium-ion batteries. Maria, please do begin.
Thank you very much, Maria. So yes, I'm going to present some work that we prepare in the group of Magnitude Rigi with all my colleagues that are here. And we work on lignin-derived electrospun mats with graphene oxide for different parts of sodium-ion batteries, as you will see, for carbon anodes and also for three-dimensional carbon collectors. So, second. So just because we work very much on materials that are sustainable or more renewable, I wanted to mention why we do this. And it's because we are working for materials for green energies, batteries. But if we want to really be green, the materials that we produce for these green energies need to be also sustainable and be produced for sustainable resources to really balance the energy benefit that we are having from them. It's like, for example, when we see electric cars, emissions, CO2 emission of electric cars are quite much lower than conventional cars, but EVs batteries are very CO2 intensive because of the raw materials, the processing and the recharging. So if we want to balance that, we need to obtain materials for these batteries that are not CO2 intensive. So it's our approach in the group of in the Tirichi group to try to get there into this balance by transforming the existing value chain for obtaining these materials. So what we propose is more of a circular economy in which we use waste as resource. And we designed this waste, we treat this waste in a way that enables us to obtain materials that are very high end, like for energy. So our question is, can we get materials that are better or equally good as the ones that are used for these technologies by employing renewable feedstocks? And one of these projects, like comprising this renewable concept, is using lignin as a renewable carbon precursor. So lignin is a very important chemical in biomass. Is the second most abundant. And lignins are normally these like the major byproduct from paper industry. 98% of lignins are burned as low fuel grade, and they have no competition with food supply. They are low cost, and we can tune the structure by the process that we use to produce them. So it's a very attractive material, and there's been recently a lot of interest and investment in producing materials from lignin. So in this line, we have produced materials, carbon fibers, electrospun from lignin, also using PO as a polymer to help the spinning of the solution. But most importantly, we've done that in water and using sodium hydroxide to obtain highly porous carbon fibers with more surface area and more active sites than normal carbon fibers that are produced from petrochemical precursors. We have obtained flexible, freestanding, low-cost, oxygen-containing surfaces with denser structures and improved wettability that we've been able to use for supercapacitors, redox flow batteries, and now we want to use them for sodium-ion batteries. But one of the most important things in these, or the major limitation that we have in these lignin fibers, is the conductivity. So if we combine lignin with graphene oxide, we have an effect of the graphene oxide that helps and aligns the chains of this very disordered lignin. And that means that when the fibers are carbonized, then we are able to obtain an improvement in the carbon microstructure with more graphitic domains and highly conductive lignin graphene oxide fibers. Literature has shown how by Raman we can detect that in these materials incorporating graphene oxide, we can, at high temperatures though, we can obtain very, very ordered structures. And here the TM shows that even at 1,000 degrees, when we carbonize lignin on its own and lignin with graphene oxide, we obtain much better and ordered structures. So we want to take advantage of this help effect that graphene oxide produces in lignin to generate more conductive fibers. So we produce our fibers, electrosponge, for the solutions that I mentioned before in sodium hydroxide, water, and using PO as a adjuvant for the spinning of the solution. And we obtain, we spun different contents of graphene oxide. And here's the collection of microstructures that we can observe by LCN. So when we observe the acid-spun fibers, we can see that by increasing the weight percent of graphene oxide, we see the appearance of these elongated features. And we believe that that is happening because the graphene oxide, due to the high ionic strength of the solution, due to the concentration of sodium hydroxide, is coagulating and partly being reduced in the solution. These features are completely disappearing when we carbonize the samples at 1200 degrees and 1500 degrees. And what we observe is that when graphene oxide is not present in the fibers, this carbonization temperature is enough for destroying almost entirely the structure of the fibers, because of the templating porous effect that gives the sodium hydroxide, which is the activating agent, and therefore also templates a porosity there. When graphene oxide is present, then this doesn't happen, probably because graphene oxide is reinforcing the fibers and gives them a stability for this carbonization temperature. Although when we go to very high graphene oxide contents, we can see that at the highest carbonization temperature, this graphene oxide tends to explode inside the fiber, as we can see here. And that is not very beneficial for our 3D freestanding maps. So we did some more characterization on Raman to see how this graphene oxide was helping the graphitization of our fibers. We can see for these three different temperatures, 1200 degrees and 1500 degrees, we can see how the D band, the ratio between the D and G band intensities changes with temperature and also with graphene oxide. And then we can see here as a summary for the three different temperatures and the different contexts of graphene oxide, the ID to G ratio, it increases first because we are talking about a very, very disordered material that we start with. And then it increases to then decrease in some of the cases when we are having the highest concentration of graphene oxide, but continues increasing for the lowest concentration of graphene oxide. This, what is telling us is that by adding the graphene oxide in the cases that we start with this very disordered material, graphene oxide is helping to promote the crystallization of these more ordered domains until a point where they start growing. We can see these by calculating the crystalline size of our domains through Raman by the Ferrari model, and we see how the ID to G ratio increases until a point where it can no longer where the defects really start being reduced, and then the domains start growing. A part of this effect, we can see how the conductivity of our lignin fibers are increasing with the increase of graphene oxide content, and also carbonization temperature as expected. And we can achieve conductivities of almost 10 to the power of 2 Siemens centimeter to -1, which is quite a good improvement from the only lignin fibers. So we wanted to use these electrospan carbon fibers for 2 reasons in these sodium-ion batteries: as hard carbon anodes and also as current collectors. And I will explain you why and how they behave good for mainly 3-dimensional current collectors. Just as a little summary of why sodium-ion batteries are interesting is because of their sustainability. When we compare them to lithium-ion batteries, which are the dominant technologies that we are currently using. So lithium is very scarce in the globe, whereas sodium is very, very abundant. So also in sodium-ion batteries, the current collectors are aluminum, which are much cheaper than those copper ones used for lithium-ion batteries. Also, one advantage is that lithium and sodium are very similar in the way that they behave, or like they have to be processed for the batteries. So that means that sodium ion technology is a drop-in technology that won't need too much of a change from that has been developed already for lithium. And of course, there are some problems because sodium is a bigger ion than lithium. Therefore, the normal graphite that we use for the intercalation of lithium ions is not suitable for the sodium ion batteries. That brings a lot of problems, but also many more advantages. And that's why we can use carbons that are produced through other routes as hard carbons for the adsorption of sodium, as I will mention later on. So starting with why these carbon nanofibers could behave well for sodium metal ion batteries, just in the case of sodium, utilizing sodium metal anode batteries, we have a very high theoretical capacity that comes from the pure sodium metal. But the problem is that when we want to use sodium metal as an anode, because of the high reactivity of the metal, when we use it with liquid electrolytes, then a very unstable solid electrolyte interface forms on top of the sodium. And that because during cycling charge and discharge, then there is the growth of dendrites occurs, and therefore there's a volume change and exposure of fresh metal to the electrolyte, and that means that we lose a lot of sodium that becomes dead after continuous cycling. So one of the strategies to inhibit this of happening is introducing the sodium into electrode architectures that can both reduce the current density, but at the same time serve as effective nucleation templates for the sodium metal. So in a way, this has been done with other materials which are not as low cost and sustainable as the ones that we are proposing, but they will behave similarly as what we can see in this cartoon here. So if we have a planar current collector, the metal will deposit on top inhomogeneously. And if this happens over and over again, then dendrites will start growing. Whereas if we have a three-dimensional porous host, this ion flux will be much more homogeneous, and then the plating of the metal will occur more evenly and without the growth of dendrites. So we have identified that there are two main important factors in how these three-dimensional current collectors behave. And it's not only about the number of defects that we have for promoting the nucleation of the metal, but also about the conductivity of the whole scaffold. So we've done continuous plating and stripping of sodium on our carbons in diglime, which is a very stable solvent, using sodium CF3CO3, a 1 molar solution. And we've seen that when we use only carbon fibers as the substrate, we can see the appearance of this overpotential, the nucleation overpotential, which shows that there's still some sort of inhomogeneity here. Whereas when we introduce graphene oxide in our fibers for the systems containing 3 and 5%, we have virtually no overpotential, which is very promising and tells us that probably we will be able to use these materials at very fast charging, stripping and plating rates, which is very, very good. So we checked what happened with these three-dimensional carbon structures after continuously plating and stripping, and we hypothesized that what is occurring is that there's a solid electrolyte interface being formed on top of our carbons that is stable and enables the homogeneous plating and stripping, and our fibers are fully covered with this metallic sodium. And we are avoiding an inhomogeneous formation of the SIA, which promotes the cracking and the formation of dead sodium, as this cartoon is showing here. So if we check on the Coulombic efficiency of 28 cycles of plating and stripping, we can see that we are recovering all of the sodium that is going in, is coming out again, which means that we have a very, very high reversibility and that we are not forming any dead sodium. If we check on the EDX of the carbon fibers, after these 28 cycles, we can see that in the plating state, in the XC to SEM, we can see the carbon fibers are fully covered with sodium, and that we don't see a huge inhomogeneity of this phase on top of the carbon. So the second approach that we were thinking with these fibers was with as carbon anodes. As I mentioned before, graphitic structures are not able to intercalate sodium, and that's why we have to use hard carbons that are produced from different sources. And basically, in the sodium ion storage mechanism, we can see two different regions: the sloping region and the plateau region. And each of these parts of the ion storage within the carbon is related to different features of the texture, the porosity, the defects, the interlayer spacing of the carbon. This is still under debate where and how these ions are stored in the hard carbons, but with our lignin graphene oxide carbon nanofibers, we've done a preliminary screening of some of the carbonization temperatures and concentrations of graphene oxide, and we can see differences. For example, when we check the discharge curves of the lignin only carbonized at low temperature, 800 degrees, we can see how we have a very open porosity here that probably is enabling the electrolyte to decompose on top of this carbon. And that's why in the first cycle here, we have a huge capacity that then fades on the second, third, and fourth cycle, as we can see here. At the same time, this capacity that remains is probably due to the enlarged graphene interlayer distances that are still large enough to enable the sodium to go in.
Maria, sorry, we're running out of time.
Oh, sorry, yes.
Yeah, I'm really sorry. Can we please wrap it up? Probably we can have just one quick question or just conclusions. Sorry about this.
So we have developed these systems with graphene oxide. We seem to have very effective three-dimensional scaffold structures for the plating and stripping of sodium, and probably also for lithium. We need to explore different carbonization temperatures and also different contents of graphene oxide, complete like the whole screening of these materials. And we are also very interested in doing Raman, in situ Raman characterization to see how the graphene oxide is affecting the sodium plating and stripping, and also the storage. And to see how the graphene oxide is changing the porosity of our carbon nanofibers and being able to tune better their behavior in sodium-ion batteries. So I just wanted to thank all my colleagues that have done this work with me, also Magda in my group, and these are our emails in case you need anything. And thank you very much for your attention.
Thank you very much, Maria. I do hope that if there are any questions, we can discuss it during the coffee break. But right now, we unfortunately have to move on to our next speaker, if you wouldn't mind. So our next speaker is Dr. Hidekazu Kuribayashi from University College London, sorry, Imperial College London, University College London. So Dr. Hidekazu is going to tell us why the magnetism and spintronics in flatland are exciting. So please, it's over to you.
Yep, okay, can you hear me?
Yes, perfect, and we can see your slides.
Yeah, great, fantastic. Thank you very much for inviting this exciting workshop and to share our latest results on this 2D ferromagnetic systems and with LCN colleagues across the 3 different institutes. So I'm very excited to hear any feedback within this session or outside of this, offline sessions. All right, so my name is Hidei Kuribayashi from UCL, LCN, of course, and then this work has been done by lots of my LCN colleagues within UCL, and also I just want to acknowledge my external collaborator in NUS Singapore, particularly in the group of the Gorky Eder. All right, let's get started. I just want to introduce a new just material group. It's just like a graphene. Of course, this is 2D material sessions. It's just layered materials. What's different between the one that has been already discussed and this one is simply have a spin. And that's because one of the, this element inside of this layers has for example, chromium. This is a famous or popular 3D transition metal to create antiferromagnets. But anyhow, it has, for example, chromium 3 plus state, and if you put this 3 electron inside of this electronic structure and crystalline field is involved, then you can create a 3 spin polarized states where we can exploit as a magnetism and also spintronics. So that's a key thing, but nothing else than this ingredient we need to use for this application. Right, so then maybe I'm very ambitious to explain spintronics within 1 page. So I probably cut off some of the important development, but this is something my personal view as a spintronics. It's basically really new material science research, and that can let a new discovery, a new function, and hopefully in the new future electronics devices. And led by, for example, we have a new crystalline structures and we normally tend to use 3D transition metals and stack of it. And for example, not only just the crystalline structure, but multi-layer can give you additional function, because at the interface, we can create a new spin transport and also, you know, extra magnetic states there. And for example, when we think about Nobel Prize winning GMR effect, it's based on this concept. And also not only just stacking on next to each other that we can do in 2D materials, but also in the lateral dimension, we can create some like a lithographic pattern so that you can create some artificial, you know, bar or allays or lattice so that we can control magnetic orientation, in this case, using magnetic dipole interaction. So that's really the material science we are looking at, and every day we try to really advance our knowledge and the capability of making the materials. And if you make some interesting materials, and then we can also control the magnetic moment. So we try to move one of these spins and then try to argue that this is a low energy efficient, no, high energy efficient electronic devices based on spin. And the popular effect is called spin transfer torque, where you have a two magnet here, and then just simply passing current through, then you can spin polarize the current inside of it by using this kind of polarizer, ferromagnetic 1, and then that can just bring the angular momentum to ferromagnetic 2, and then this amount of angular momentum is high enough, then you can actually rotate or switch this second layer. And that's what we call spin transfer torque. And also the creation of this group of spin polarized current can be done through so-called spin Hall effect. This is originated from spin orbit interaction between the materials of any. And these two effects can actually try to switch the magnetic materials by electric current, for example. And if you're doing this business very, very efficiently, what we can foresee is that we can make a very high efficient memory devices, for example. This is a conventional so-called magnetic LUM, and then this is already commercialized. Right, so this is just a kind of spintronics field from the material science to the device application. And then when we try to imprint 2D materials, for example, we can replace this crystal. Again, we have a very low symmetry crystal in here. And then also, if you try to make a stack, then you can just do, as Antonio already nicely explained, so we can have a full choice of stacking on one to the other without any constraint or lossless matching and so on. And also in terms of lateral, you know, lateral arrangement, not only just patterning it, but also we can make a, you know, like just try to shifting this stack so that we can make a more lattice, for example. And in this case, compared to the previous case, we have a magnetic, you know, dipole interaction that plays a role. But in this case, it's more like a low short range exchange, and also correlation could be playing a role in the future. So that's something we are really excited about to make it happen, but we are just in the process of doing that. Right, so then just a bit more like fundamentally, also I just want to raise lots of few questions, such as how magnet behaves in a really truly 2D limit, and also how to describe the spin wave excitation in that regime as well, and also how spin transfer through this 2D limit, whether this is different from the 3D limit and so on. These all fundamental questions should be also addressed or answered by doing these kind of experiments using 2D ferromagnetic materials. And then we can also excite this 2D ferromagnet by a different external stimuli. So just a few things that we want to do in the next few years, or even just 10 years time. Right, so then what exactly we have so far as a la carte of this 2D magnetic material. So this is just a famous, I just want to introduce two famous ones. Number one, this is a chromium germanium telluride. Again, this is just the stacking of the layered films, such as this is a top view of it. And then this, I think, blue one is a chromium that carries angular momentum. Then through these tellurium atoms, we can have some so-called super exchange coupling between these two lots of different tellurium atoms there, chromium atoms there. Then when we exfoliate, so this is more like a worm-like structure, but this is something we can do. Then we can just check that, layer, this is second layer, and this is third layer and fourth layer. You can tell that different layers within the single block of these materials. And then by using magneto-optical measurements, you just zoom into the specific region locally by shining a laser, then we can try to see how magnetism is sustained from the bulk region down to, in this case, the bilayer region. So this is a typical, car rotation measurement as a function of field, and you can see that some sort of hysteresis, a little bit hysteresis loop, we can see that. So that is the development actually published in 2017, and at the same time, it's the same, similar material but different cross material. In this case, this is 2D antiferromagnets, or I just want to explain that. So this magnetic ground state can be controlled by just a number of stacks. So when you have one layer of it, again, chromium moment can be polarized and then have a ferromagnetic state. They just try to align in the same direction. Now, when you just add extra layer on top of it, what's going to happen is, in fact, the second layer want to polarize in the antiferromagnetically coupled to the one in the first layer. So this is just the schematics of it, and then you can see that then the first maybe up to we apply about less than 1 Tesla, then these two are polarizing up and down and up. This is the two different states, and then when you just apply large enough in the perpendicular direction, you just flip the one of the spins into the one direction so that it's tend to be a ferromagnetic phase. So this is because the interlayer coupling exchange coupling between these two layers is reasonably weak because of the van der Waals gap. So this gives you extra tunability due to this gap. And then you just put the third layer on top of it, then again we can recover back the ferromagnetic state. So that's really exciting. This is something we cannot do with a conventional crystalline materials and so on. Right, so then this is just the two of this. This is actually, these are the two insulating layer. I just trying to find it, but I couldn't find it. But anyway, these are the insulating layer that I explained. But it's just a whole different group of these 2D magnetic materials. As you can see that if somebody asks me that is there any material that can work at the room temperature, we'll start seeing a few materials that can meet that kind of conditions just after a few years of the discovery. And also, therefore, in the next couple of years, or just 5 years' time, it is not surprising that many magnetic van der Waals material can work at a room temperature. So that's I think something we are expecting. Okay, so then, so I just want to explain that it's a whole range of different conductivity we can pick depending on the choice of materials. If you want to work on an insulating regime, so some of these I already explained, but if you want to work on the metallic regime to just work on spin transport, then we can still have some material to be available to meet your interest. And in terms of just basics of magnetism, what I can explain is if you just really localize magnetic ion as an insulator, so the exchange coupling tend to be more like through other elements. So this is what we call super exchange coupling, and then this spin is purely isolated, so that the description of Heisenberg picture would be very, very suitable normally. And then when you start doping, then now you start populating this charge carrier. And then some of the exchange coupling mechanism can be done through this charge carrier. So it's basically these two magnetic ions are communicating through this spin of this charge carrier. So this is what we call double exchange coupling or RKKY interactions. And also, if you just fully doped and we just Fermi level is within the band, then what's going to happen is that we tend to believe that these are suitable to the description of the itinerant material, so band-like picture, and we can just discuss about Stoner criteria and also Pauli paramagnetism. So what we can do with these materials is that by changing this conductivity from insulator to metal, and then the question is, well, how we control this magnetic exchange interaction, and that's the motivation of our latest work. So that's the motivation. So the material that we use is chromium germanium telluride. I just call it CGT from now on. So this CGT is just a ferromagnetic semiconductor. You can see the gap in here. And again, this is the layered materials, and then exchange coupling is through this tellurium atoms. So this is a super exchange mechanism. And we try to gate these materials as already Antonio explained a little bit, and try to see how magnet is changed depending on this gate voltage. Okay, so that's the things. So then this is like a schematics of our device, and we just have this CGT, and we just put the contact next to it, and then we put the ionic gels. This is like a nice electrolyte so that we can apply a large amount of charge accumulation through an interface. So that's a bit typical for this 2D material community. Now, then this is like a FET structure. And then when we apply the voltage, so we just applied a few volts, plus and minus, then what's going to happen is at 0 volt, we don't have any significant source drain current. But once you increase the voltage up to probably close to 4 volt, you can see really nice current going through this channel. So this is just turning on of the FET structure, shall we say. So that's the case. And then we start with 20 nanometer of CGT. So this is reasonably thick. It's not like a few monolayer regime. But what we discovered is well, at this doping regime, so we accumulate so much charge carrier at the surface, but then when we calculate this, the depth or width of this accumulation, then we discover that this is almost like 1 nanometer of the charge accumulation region. So this conduction is happening just top 1 nanometer of the CDT material. So just starting with 20 nanometer, but effectively we create a monolayer two-dimensional electron gas by the gating. So that's an interesting point. Right, so then this is the resistance versus temperature. So you can see that 0 volt voltage application, this is more like semiconductor insulator behavior, but once you apply high voltage, then you can see that this is the metallic behavior, which is great. And then from this whole resistance, then we can calculate this charge accumulation, which is reasonably high. This is just 10 to 14 per square cubic centimeter. So that's reasonably large, shall we say. So that's great. And then let's look at the magnetism by the magnet transport. So this is just a measurement of magnet transport as a function of this applied magnetic field. So just moving back and forth of magnetic field and see how resistance change. And the only thing that we want to know is, although this is a really jumpy behavior, so which is depending on the domain wall propagation, nucleation, which is very complex. So I don't want to talk in great detail here, but hysteresis is sustained up to 180 Kelvin. And against the bulk Curie temperature is 64 Kelvin. So from that, what we can tell is that already Curie temperature is enhanced more than 100 Kelvin by the gate application. And so this is just out of plane scan and repeating the same experiment by changing it out of plane. Again, this is a bit more spintronic-y, but I just want to tell that this is out. The fact that we can see a large hysteresis in out of in plane, and when you bring this moment out of plane, so moment in plane here, this angle is 0, then we can see that this is the in plane favorable materials. Okay, so then we just plot this. So one thing I just want to mention is that we just discussed from now on that this magnetic field point where this switching is completed, so that's something related to the magnetic anisotropy and something related to the magnetism. So that's a plot of this data. So you can see the pristine material without gate voltage. This TC or this dies out around 60 kelvins. But once you increase the voltage And we can see that this parameter goes up to really high value. So that one thing we can tell is that this is changing that sign, which means that also easy access is changing from the outer plane to the in plane. If I have time, I just can discuss a bit more later. All right, so this is just a demonstration, just sitting on 170 Kelvin, applying 3.1 voltage, if nothing happens, but as soon as you apply 3.9 voltage, just up to like by 0.8 voltage, you can see that we can create the magnetism. So just switch on and off of this magnetic behavior by just applying the different voltage. So that's nice to see. Okay, so the interpretation of this is that, as I already explained, that this is the insulating or semiconductor behavior, but once you just dope and the charge moment, then you can really go into this Fermi level, is going into inside of the conduction band. In this case, we can populate a lot of conduction electron inside of this conduction band, and then that can promote and hop around, and that can really facilitate the double action mechanism. And then because of this kinetic energy reduction, then we can just reduce the total energy as a whole. That's the driving force of the ferromagnetism within this doped regime.
We're
right.
Almost out of time.
Yes, I have 2 minutes to go. So I just want to say that this is also calculated, supported by the DFT calculation. And finally, I just want to spending 1 minute to explain. I just switched a completely different topic, but within one slide. So using not only just working on the electric field, but we try to measure real spin dynamics in the monorail regime. Still, this is a work on progress, and using, well, thanks to just a superconductor resonator, very sensitive resonator made by John Morton's group and the colleagues through this quantum technology initiative, then we just make this resonator and putting the 2D material on top of it. Then we just try to listen and we'll listen how this spin wave is excited. And then we just try to this is, I'll skip everything through, but what I can highlight is that this spin magnetic relaxation rate is actually better in the thin film regime. So this is very pleasing to see. And we are excited about what happens in a really truly one monorail regime. So then just wrapping up, this is a summary. So I didn't answer the question, is that exciting, the 2D materials in the spintronics, as spintronics, the magnetic in 2D material? Yes, definitely the answer is yes. And we have lots of flow opportunity of this material science and new excitation method, and also just a new level of physics that we can enter. So thank you very much. And I'm very happy
Thank you, Hidekazu. Thank
you.
Yeah, brilliant talk. Very good overview. If we have any quick question from the audience, I think we have a minute. If there are any raised hands, no. Oh, well, I would suggest to discuss this topic a bit more during the coffee break, maybe, because we really need to move on to our next speaker then. Our next speaker is Dr. Riccardo Sapienza from Imperial College London. So we would have to give him the floor. Riccardo, are you here? Yes, you are here.
Yes, I am here.
Good to see. Good to see you. Yeah, so I think we could see you and probably your slides. No, not yet.
Not yet. 1 second.
Not yet.
And here they are.
Yep, everything is working perfectly. Okay, over to you.
Okay, fantastic. Thank you very much. And thank you very much for having me here. It's very interesting to see how many different takes we can do of the 2D materials. So our take is about the photonics side. So this is probably, I don't know if I'm the only speaker, but so far I am the only speaker that will introduce photonics. So I will take it a bit slowly. So this is our group in Imperial. I will mention again a few people that are involved, but this work is coming from a very engaging collaboration with Sasha Tartakovsky in Sheffield, and with Stefan Meyer, that is half here in Imperial and half in Munich. And so in our group, we work on light in nanostructure materials, and this goes from network-like material that you see here on the left, where we use them to construct modes of light and make laser, to nonlinear optics at the nanoscale, as you see here in the middle, and to single emitter spectroscopy. And in all those kind of topics, 2D material can play a role. won't go into all the details, but this is my one slide to summarize why I like 2D material, in particular TMDCs for photonics. So they have a very interesting properties as light emitters. So they can emit light as delocalized exciton or localized defects, especially when strain is induced. And this is still a topic that open, and there are many interesting discussion about that. They're very interesting for nonlinear optics. This is the paper that came out last week from the group of Cerullo, where they measure I think optical parametric amplification from a single layer of TMD. And they also are very useful as a material themselves to construct optical resonator. And the reason is that they have very high refractive index, reaching up to 5 in the visible range, which is one of the best material that one can find, which is not very absorbing. So they can be used both as a medium to construct optical devices, or the medium to generate nonlinear phenomena, or the medium that emit lights. And in my talk, I will talk only about the light emission part, which is what we've been investigating mostly. And I will start saying, so I will discuss mostly the WSC2, and I will start saying that WSC2 is actually a very bad emitter. And this is a very good thing. Let me explain you why. So it's a bad emitter in the sense that a single layer emits as a quantum yield of around 0.1%. This means that I need to send 1,000 photons or excite 1,000 times the material to get 1 photon out. So this is bad in the sense that this is not a very bright material, but it's also a good thing for us because we know very well how to enhance material that are not optimal. When a material is already very bright and has a quantum yield of 100%, it's very hard to do something about it. But instead of when the material is non-optimal, like in this case, then we can use nanophotonics to enhance it. And then we can benefit from the material property, which is the fact that it's a layer, the fact that we can structure it very well, that can be interfaced with other material, but also we can make it into a very bright medium. And what I will show you at the end, this is my last slide, as also the first slide. We will, I show you how we're coupling a single layer to a nano antennas. This is what you see here. These are 2 discs very close to each other. And the scale here is around 1 micron. We can enhance the light emission from the WSC2 by around 4 orders of magnitude. And so this is all done through a nanophotonic design. Right, how do we do that? So before I reach that level, I need to introduce a few concepts. So I will try to do it in a very didactical way. So first of all, the emission of light is not just a property of the material, but it's a property of the material and the environment. And the reason is that the emission of light is the exchange of energy from an electronic excited state and a photonic state. So we need to have electron state, and this typically come from the material that has transition, but we also need to have the photonic states available for the process. So as it is a process that is an exchange of energy, you see here in this equation that I put here, the decay rate, so the amount of photon per second that we get from the material, depends on p square, which is the dipole moment of the material, so the material property, but also depends on the density of state, this rho function, which is the density of state of the medium that embeds the source. And this means that if I take an emitter and place it in an environment with 0 density of state, it will not emit light. But if I put it in a place where very high density of state, the emission rate will be enhanced and the material will be brighter and brighter. So this is the so-called Purcell effect, which applies to any kind of transition, not just optical. And even if it looks like a bit an obscure phenomenon, in reality, you probably experience it in your everyday life when you move around the city with your mobile phone and the signal goes up and down. Is because your phone is probing the density of state at your phone wavelengths. So this is a very interesting approach. This is at the heart of many nanophotonics design. So by placing an emitter in the right nanostructure materials, we can boost the emission rate and the brightness. And the goal here is that we take an emitter which has its own property. Now here it's drawn as a molecule, but it can be any emitter. And then by placing it in the right photonic environment, we can make it into a sort of super emitter, an emitter that has much higher quantum yield, which can approach 100%, that could be stable, typically enhancing the photonic transition. We are decreasing the probability of going into dark states or blinking or other processes. And therefore the bleaching also is reduced. So the photonic process will be more and more optimized. And also we can make the emission faster and faster, which means more photon per second. And in some cases, it means also an emission faster than the coherence time. That's at least in theory. How do we do that? Well, we traditionally, this is done with optical cavities by placing an emitter between two mirrors, in a ring resonator and so on. So in this plot, I'm plotting the size of the optical cavity versus the Purcell enhancement, so what I call the local density of state. So you see that when I make the resonator smaller and smaller, what happens is that we lose Q value. So in some ways, we trap the light for less and less in this resonator. So we lose the temporal confinement. And therefore, often this was thought to be a bad way. So usually you want to go to larger size to get more, a stronger effect. But if you go on the smaller side, there is a moment that you cross the red line, which is the wavelength of the light. And when you go to the nanoscale, then suddenly you can design structure that instead localize a field into smaller and smaller volume. So you lose the temporal control, you gain spatial control. And when you do that, you are enhancing the optical interaction by basically squeezing the light to volume smaller and smaller, closer to the size of your dipole, which is always of the order of nanometers. And so in this way, you can see that this curve goes up again, and the Purcell enhancement can be very high. And this is the regime, of course, where we are interested to work. There are many ways you can make nanocavities. The most common one until a few years ago was to use metal particle, the so-called plasmonic. I won't go into the details, but this is using the oscillation of metals at a frequency of the light. And instead of what we have been working the last few years is to use dielectric structure. So these are high index material, and our favorite is gallium phosphide, which are designed to confine the light internally by what we call the mean resonance, which is the interference of the light in the particle. Now, at the beginning, and you see in this slide, the plasmonic was much better, was reaching 1,000 enhancement, whereas the electric were at the 10th level. But this is something that one can improve, and this is so far still only a theoretical work, but we have designed an antenna that can enhance the emission of light by around 800 times. And of course, this is done by changing a bit the way we design them, and there are more information in this paper, but I won't have time to discuss it now. But what I want to say is that to do that, to achieve this black curve here in the middle of the plot, which has a resonance around 700 nanometer, we need to use the black antenna that you see on the top right, which has a very strange shape. And in particular, has a very small gap in the middle. So these small gaps is around 10 nanometer in size. And this is one of the key challenges that are in nanophotonics. So to actually exploit this antenna, we need to put our emitter inside that little gap. And this is very hard when you do with a molecule, because nano positioning is really difficult. But this is instead something that we are trying to explore with the use of 2D material, because in this case, the 2D material can be designed in a way, can either be conformally over these antennas, or even we can create a local defect at the position of the gap. And this is something, you see, the 2D material for us in photonics doesn't come as just another emitter. It's a different family of emitter, which we can manufacture and engineer and play with in a different way. So the second aspect that we need to use to understand how we can enhance the light is to think about nano antennas. And so here, what I want to is to use a nanostructure material as a way to connect the far field of propagating waves with the nanoscopic size of our emitter. And the reason why I need to use an antenna is that if I take a dipole, and this works for any dipole, so this could be from a 2D material or from a single emitter, and I place it on a high index substrate, which is our typical substrate, which is here the blue part, then this emitter will emit light mostly inside the substrate at a very large angle, close to the critical angle, which are angles that typically are very hard to collect. So what's happening here is that the light goes into the glass and never escapes, and so we don't have much signal. And this is an experimental reason. Now, if you were to, in some ways, embed the material in homogeneous medium, then you still have a spherical wave coming out from the dipole, which would be very hard to collect because it would be spread in all directions. So you really would like to be able to communicate with the emitter and send light from one direction and receive it from the emitter. And the way we do that is by using nanoscale antennas. And these antennas are made in many different ways, but here is probably the most striking one, which is it's a Yagi-Uda antenna, which is very similar to the one that you can find on the roof for TV waves. Now, this is a nanoscale version, and each of these gold bars is around 100 nanometer in size. And similarly to the one on the roof is formed of different elements, and in one element you need to put your emitter, and then you will have the light going in the direction of the Yagi-Uda antenna. In this case, it would be going leftward. Now, this is one of the antenna, but there is a large family of nano antenna that's been designed. And as you see here, I'm plotting the size of the antenna on the horizontal axis, and the vertical is the directivity. So how much light is directed. So a larger directivity means a much more beam-like emission from the antenna. And you see that there is a clear trend in the large scale. The larger the antenna, the more directional. This is similar to conventional antennas for like a parabolic dish or similar antennas. But there is a moment that, again, there is here a gray line, which is the wavelength of the light. When we go to the left side, we are at the nanoscale. And there you see that we have many different design, metallic, dielectric, hybrid, and they all have quite a good directivity of the order of 100 to 1,000. And so you see, there are ways that we can extract the light very well from an emitter by using this nano antenna. Okay, now I can put everything together. So we did this work together with Sacha Tartakovsky. In particular, this is the work of Luca Sortino, who was a PhD in Sheffield. And on our side, Sandro Mignuzzi did most of the work. And sorry, I don't have the picture for Javier, but so Javier Cambiaso was also very involved in this project and is from the group of Stefan Meyer. So we took this two-dimensional material and then we placed it on gallium phosphide dimers that you see on the picture on the right. These are a few hundred nanometer in size, and which we made by electron beam lithography. And then we placed the 2D material on top. And doing so, you can see on the picture on the left, which is an AFM picture, we cover conformally the nano antennas. Now, the electric field so the antenna interact with the light very strongly, and they confine the light. And you see here on the plot on the right that the field is much higher inside the antennas. You see on the order of 23 times more inside. But so this would be the ideal place where you would put your emitter inside, in between the two discs. This is very hard to do, but the good side is that you see that the field leaks outside a little bit. And so when we place the material on the very top of these antennas, we are still coupling quite well to the antennas. And you see that there's a field enhancement just on top of the antenna. And then I wanted to break down the enhancement that we get in different parts. So this is then the result of the experiments, and I will use the theory to guide you. So here we have first a Purcell enhancement of around 15 due to the effect of the density of state. So by using these nano antennas, we can enhance very much the density of state. Now, this is very important because not only we are increasing the decay rate, but also we are boosting the quantum yield of the material again, because the quantum yield is very low. And so we have a much larger quantum yield because we are enhancing the optical processes with respect to the non-radiative processes. You see here that it's not homogeneous everywhere. So you see that there is a much higher enhancement very close to the antenna. But on the other hand, it's fairly flat in the middle. And so overall, we have a 15 times enhancement. Then we also, the antennas act as an antenna for the excitation, meaning that when we send the light into the material, the antenna will focus the light down to the emitter. So this is the so-called antenna effect that I picture here on the left. So our light beam then is focused very well into the volume around the antenna where the 2D material is. And this gives us 150 times enhancement of the efficiency in exciting the material. Then we also extract the light more efficiently with the antenna. So this is the reverse effect. So now the emitter, so the WST2 emits the light, the light is coupled to the antenna radiates the light out of the sample. And you see here on the plot on the right that if I don't use the antenna, I will have the black line that you see here, the very little circle. But when I said I use the dimer as an antenna, then the intensity, you see this is a polar plot, so it's a lot brighter, and now it's picked outside of the sample, which is the good side, the side where we can collect. And so here in this way, we get another 15 times enhancement in collection. And then of course, so if you put all together, and this is the summary here on the bottom on the bottom curve. You see this is the summary of all the enhancement that we get. So the excitation, local density, and which is quantum yield, and collection. You see that we can get to an enhancement of the order of 4 or 5 orders of magnitude, which depends, of course, on the size of the antenna that we're using. And on the top, you see the same enhancement, now experimental. And you see that there's clearly a spread, and this is a log scale, but you see that the trend is similar, and we do get very large enhancements. On the left, I'm plotting the confocal scan that you can do over the sample. You see that the antennas are in different parts of the sample, and on top you see the layers, the one layer and the bilayer. And you see that the announcement is very clear. Even visually, you see that there is a lot more light coming out of the sample. So this brings me to my conclusion. I may have been a bit fast, but I think the chairperson would be very happy about that.
Very good.
Our take of using two-dimensional material and TDM DC in particular for photonics is varied, and there are many different aspects. I just touch upon one. I still believe that we are at the first steps of those kind of materials, and we are very much using the fact that the communities, and that's mostly you probably, are developing so much those materials, mostly for electronic properties, that we can really now have very high quality materials, which we can exfoliate very well, very large, which can be used either as an emitter when they are on the monolayer level, or as photonic structure when they are very, very big and bulky. And this is something that will develop more and more. And I hope this will give us the capability of generating local quantum emitters at specific position, where we enhance them with all our nanostructures, and maybe coupled to electrodes and gates and similar. And so this could be, for photonics, a very important next step. And with that, and of course, we want to have a bright, stable, stronger, faster emitter. And with that, I thank you for your attention.
Thank you, Ricardo. Brilliant talk. And we have questions. So we have a first question on the chat from Neil Alford. Could you please probably unmute yourself? So the question is, wasn't sure if the antenna is electrically short, and if it is, what is the efficiency?
If the antenna, sorry, is electrically?
Okay, short. And if it is, what is the efficiency? It's the question from Neil Alford. So I think we can, Neil, if you could unmute yourself, we can just have a discussion.
Yeah. So the antenna is purely optical, so there's no electricity in any way in the system. And so in optical terms, so this is an isolated resonator. So wave comes from the far field. So if you want in a circuit picture, that would be the input. And then the antenna is driving the local fields that then radiates again. So we call it an antenna because they have the same functionality as macroscopic antennas. But they usually...
that's great. Can you describe an efficiency though, perhaps with this or not? Or is it completely different?
I can. So the efficiency would be, for example, if I have a quantum emitter emitting one photon, and then I would say how many of these photons couple to the antenna and then radiate out. That would be the equivalent efficiency. Now, this number, we never think in this term, okay, I have to say. Right. So we always think it the other way. So we drive the emitter continuously, and then we look how many photons we get. And so in that case, in our receiver, we will get 10 to the 4 more photons. But that's because we over-normalize to what would happen to the emitter in vacuum. We never have an absolute terms of input energy.
Okay, thanks.
Yeah, I never thought about that. I think it's not very high anyhow. It would be probably a few percent or 10% maybe.
Okay.
Yeah.
Great. Do we have any other questions from the audience? Maybe no.
I have a question.
Sure.
So it's something I was thinking. Maybe it's completely impossible. Maybe it's just stupid. But I was thinking, you were saying that one of the main challenges is to actually get the molecules we want to emit in the right spot, basically in between the two rings.
Yes.
And so my question is, could it be possible, because you showed us in the picture that the electrical field is enhanced in the middle of the antenna, basically. Yes. So my question would it be possible to have a stronger magnetic field in the middle of the antenna, and then maybe have a functionalized emitting molecule that could be drawn in the exact position by this enhanced magnetic field, so that the magnetic field does the job for you, basically?
Yeah, so these kind of approaches has been attempted in various ways. So you don't need a magnetic field. For example, you can use an optical force, like an optical tweezer, because where the field is high, you will attract dielectric particle. You can use a chemical effect, so you can functionalize the structure in a way that the molecule prefer to be attached in the middle. So there are many of those attempts, and sometimes they work better or less, but they're always very, very hard. So they all rely in double lithography, so creating another lithography to create a little hole, a nanoscale functionalization. They're all driven by surface effects. So at the moment, so if you want to have a single emitter in a specific point, there are papers out that do that, but they always, if you talk to the groups, they have tried for a few years and they got once it worked. So it's not something that we can do very well. All of those techniques have troubles. And if you look at this antenna, for example, we have a 10 nanometer gap there. Having liquid going inside this gap, it's really hard, even purely to functionalize it. So that it is a really open challenge. There are many, many different ways you can think, and there are many people trying it, and I'm sure there will be more and more. But the 2D material has the advantage that you don't have to do that. So you can coat the structure, and then, for example, induce strain and in the middle, and that could give you a quantum emitter, for example. Or in this case, the exciton everywhere, so you have them on the surface. So I'm trying to find an easier solution because the problem is challenging.
Thank you very much.
Thank you.
Brilliant. I do believe that China Nelson wanted to ask something. I've seen a raised hand. Is that true? No? Do you have any other questions? Yeah.
I did have a question.
Yeah.
It's not
Yes,
desperately
sure.
it's not desperately important one. I was just curious about because I know this is all about enhancing the emission, but my question, Ricardo, was what is controlling the choice of the molecular emitters you use? Do they just happen to be things that are very well characterized and have a high PL quantum efficiency, or are there other properties that you want to look for in this application?
So I think here we were using 2D materials because of the fact that they can be very thin. And so if you were using, for example, a lot of molecules, we would fill up a large volume, then you get a very average effect. So many a molecule will be not coupled to the antenna.
So but in your images, when you show the structure of a molecule as kind of the emitting thing, yeah, was that just a slice of material? Does it mean anything?
So in reality, this molecule in this picture is DBT. And no, I didn't want this picture. Probably I shouldn't have used it. So this molecule is a molecule that is very good at cryogenic temperature. And one of the few a molecule that, and so this is for another reason. But in general, we want a stable emitter. And in reality, we don't want a very good emitter because we enhance better low quantum yield emitters than good emitters. In a good emitter, we can't increase the quantum yield. It's already 100%. So many effects for us are driven by the capability of isolating one molecule with respect to the environment. And so when the quantum yield is poor, the environment has poor quantum yield, but the one in the middle will have high quantum yield. So that's the way. But I have to say that for us, the driving here was to explore the 2D materials and how we can control it. And then we also are now following up with some experiments to create single quantum emitters, creating strain defects. But what I show you today holds for any kind of emitter. And it works in a excitation. So we can enhance the brightness, but also the absorption. So in principle, you can have a much more absorption of light from the emitter. Now, of course, this is not very helpful to make a solar cell because you want to have a large area. You definitely don't want to have one molecule super enhanced and the rest not. But this is nanophotonic structure mediate exchange of energy between light and the material, and so they work in all directions. So we can enhance any molecule, any quantum dot, anything, perovskites, and anything can be enhanced with photonic engineering because it's sort of a separate part. So we're not working with electronic states, but with the photonic states.
Okay. We can talk separately maybe sometime.
Yeah.
Absolutely.
Okay, great. I do believe that we still have a couple of minutes of our coffee break just to stretch a bit and reconvene at 4:40 for the third session. I would really like to thank all of our speakers today. Do we have any other questions for other speakers? Maybe like while we have, I don't know, 2 minutes of the coffee break. No?